Hello interwebs, welcome to Let's Fix Computers. I've got an LG Gram laptop here that apparently has no power. So this has come in from another shop. So while I do want to plug it in and see what it does first, I think I'm going to take the back cover off and just do a visual inspection on the inside to make sure we don't have like a mangled charger port or something horrifying like that. I will do an early intro roll this video while I figure out how to get these screws off. We've got some little caps over the screw holes, and maybe these rubber bits need to come off. Awkward pause while I look around for my prying tool. Nope, fingernails to the rescue. Yep, they've got hidden screws. So I'm going to get this back panel off, we'll have a look on the inside, and we'll get started. I'm kind of offended that they called it the Gram instead of the Graham. Another insult in my general direction. The fact that Americans can't pronounce the name Graham properly as it is pretty offensive to me. But now they're not even spelling it correctly. Whoop. High energy density battery. I like those little covers over the speakers. That's a nice touch. Keeps the schmutz out of those. Wow, interesting how you can see how they've actually put in a lot of work in weight saving here. The motherboard is pretty thin, and it's got cutouts anywhere where they can have it. And you know, just yeah, they've really gone to town to keep the weight down on this laptop, which makes a lot of sense. And you know, it works. It's a lightweight laptop, this thing. It's quite impressive. Neato. Alright, well, I can't see anything screamingly wrong, so let's get the Paul Daniels meter up on screen, and let's plug in a Type-C cable and see what it tries to do. Alright, here we go. Bam. Okay, so we've negotiated 20 volts from the charger, and we've got... Look at those little spikes along the bottom with the current. That looks like something oscillating. I'm going to immediately grab my phone and my thermal camera and see if I can spot anything there, because that looks like something pulsing on and off very quickly. This is where the Paul Daniels meter is really good, because you wouldn't catch that with anything other than a high sample rate meter or an oscilloscope or something like that. So, you know, shout out to Paul Daniels and his amazing meter. Like the actual meter itself, like the display on the actual meter itself doesn't update fast enough to show this. However, that's not what that display is for. It's the software that shows you the real details with this thing. Okay, and if we bring the thermal camera in, we've got a big flare up over here on that chip there. Anything else going on? Got a little bit of heat over here as well. I think that's just that's ambient. Something is powered up there, but I don't think it's doing anything. However, yeah, this guy, that's where the show is. What are you doing? Are you burning? It's not burning my finger, but the current draw isn't high enough for that. But there's definitely something going on there. Alright, what is that? Let's find out what that is. If I come down on the macro lens, you can actually see the power pulsing on that. This is the P2 Pro. This is the Infrared P2 Pro thermal camera with the macro lens I'm using. Pimping all of my toys today, everyone. Alright, anyway, you can see what's going on there. Something's not happy. Okay, I'm going to pull out the customer's SSD there. So that's the regulator that's doing stuff. We need to find out what that guy is. It's perilously close to the CPU, and that would normally be a cause for alarm. But also, like, that's the motherboard. This is empty space for connectors, and this is... I mean, there's some support stuff over here, I guess, but that's mainly the Type-C management stuff over there. So... just because this is right next to the CPU doesn't mean that it's actually going into the CPU. although that's not impossible. CPU V-core is probably these guys over here, because these are actual power stages. My guess is that this is the 5 or 3 volt rail. So we need to figure out which one it is. We've got a tiny little 0 ohm link next to it. Let's get the multimeter turned on. Black probe on ground. And let's check the inductor for that regulator. 1.6 kilo ohms. All right, well, that doesn't seem problematic. What about that 0 ohm resistor there? 220 kilo ohms. Okay. Big capacitor. $70 kilo ohms. Yeah. So it seems like the output from that regulator isn't shorted. So why was it pulsing? Perhaps something downstream of it is faulty. Okay, I'm going to just stab around some other places on the board. Just other inductors. 40 ohms. That doesn't seem very high. I don't know what any of these inductors are actually for. I'm just looking at secondary power rails. Probably the battery charger down there. Kilo ohms. CPU V-core, because why not? 18 ohms. Yeah, that sounds about right for a modern laptop. CPUs used to be super low internal resistance, but the newer ones seem to have a higher internal resistance when they're off. I don't know the details on that. Someone in the comments might confirm, but yeah, we're starting to see on more modern systems like this, it's now quite common to see the CPU at a higher resistance. I mean, obviously, like, what was that, 17, did I say? Yeah, like 17, 18 ohms, that's still very low, but that's not like the 2 to 4 ohms that we used to see, which could very easily be mistaken for a short circuit. All right. Oh. Check that. Megohms. Megohms. This seems to have changed as capacitors have discharged after the laptop was powered up. So I think these 0 ohm links coming in, I think that's coming in from the main power rail, and those are 0 ohm links going into the regulators, acting as fuses. So that's our main power rail in all probability. Right, I've just realised I was doing all of my measurements with the battery connected, so that may have thrown them all off. So we're just going to check those again. The battery's probably flat anyway, but... Right, let's try plugging in the power again and seeing if there's any voltages appearing anywhere. We have to be a little bit careful applying power when we know there's a fault condition, because it might be suffering damage. However, there's not really enough current draw here, so I think we're okay. Right, let's see if we can catch anything. Okay, so as you can see, the voltage from this regulator is just going wild. It's oscillating wildly. Is anything else here powering up? Nothing there. Nothing there. Okay. Well, I wonder what would happen if I disconnected the inductor. Ideally, I don't like lifting inductors for a regulator like this because the feedback is probably coming from the other side. I would like to find that we go out of the regulator. I'd like to find that we go out of the regulator into the inductor, and then from the inductor we go through like a jumper or a fusible link or something like that, and then we could clear that jumper instead of lifting the inductor, because this is part of the regulator effectively. It's a component of it. But if we lift that up and we find that it's still doing wacky things, then maybe that will give us some information. So I'm going to try my luck with that and see how we do. So I'm going to start just by applying some fresh solder to each side of it, and then I'm going to try and lift one side. Alright, let's see what happens now. I don't know what I'm expecting from this, but... Blammo. Right, we're not seeing the weird oscillations now. We've got a steady 30 milliamps. So that's something. Let's have a look and see what kind of behavior we're getting. So if I measure the other side, the open side of the inductor, we've got 1.4 volts. So that could mean anything. A buck regulator like this has a feedback line that connects to its output after the inductor. It watches this output to see what voltage is coming out of the regulator and then adjusts itself up and down accordingly until it hits the target voltage. Because we've lifted the inductor, the feedback line is disconnected, so the regulator can't see its output. So it's defaulted to a low or minimum output state to make sure that nothing goes wrong. This is why we're seeing 1.4 volts. What about the other regulators? Are those doing anything? No. No. Okay. It's entirely possible that the laptop needs this guy to come up before it will do anything else. Fine. I'll unplug the power and I'll just see if we see anything interesting resistance-wise with the inductor lifted. Not really. Yeah, this doesn't really tell us much. We've got a regulator that's not starting, but it's not showing evidence of being faulty either. But I can't see anything downstream that's wrong with it. I wonder if we've got any others that match it. That's a TI 51393. TI 51395. So that one's not the same. What about that guy? No, that's different. There's another 51395 there, but this one being 51393, I don't know if those are compatible or not. They're extremely similar, but I'm not brave enough to try and swap those out. I guess we could go for a blind replacement and hope for the best. But again, there's kind of no reason to believe that there's a problem there. Let's see if we can figure out if there's a fault with this. I'm going to go into diode mode. So this is a buck regulator with an integrated MOSFET. So that means that we've got input pins here. We've got a gate drive, which I think is pin 1, and the output pins down here. So if we measure from the input to the output, then we will be measuring from the source to drain, or vice versa, depending on whether it's an N or P channel. I'm not sure which it is without looking up the details, but if we just try taking some blind measurements, we may be able to determine this. We should find that we get a diode drop in one direction. Whoops. So that's showing open line. Okay, so if I swap my probes around, there we go. There's a 0.46 volt diode drop. So that's behaving as we would expect a MOSFET to. We've got a diode drop in one direction. Okay, so far so good. Don't worry about what looks like bridges here. These first 4 pins are all linked together. What about from the gate then? I believe that the gate is pin 1 here. So let's see if we've got anything through there. Open line. Okay. And swap my probes. .6. Okay, that seems healthy on account that it's not open, it's not a short circuit as such. I'm on the edges of my electronics knowledge with what to expect here. I'm just going to measure from there because it's easier to get onto there. And to here. Open line. Swap probes. And open line. And I think, again, that's to be expected. So the internal MOSFET of that regulator looks normal to me. We're not seeing short circuits between the source and drain or the source, drain, and gate. So at this point, and that's kind of indicative because when we measured the resistance at the inputs and outputs, we saw a different number on each one. So that's kind of what I expected to see. And this kind of supports the idea that we've no reason to believe there's anything wrong with this regulator. Even though that's the chip that is getting hot, we've no evidence that it's failed. It looks like something downstream of it has a problem. But because there isn't a short circuit, we don't really know what. I'm going to put down this inductor again because we're not proving anything by having it disconnected. And I'm going to plug the power back in just to confirm that we still have the same fault that we did before. Yeah, so there's our little oscillating pulses again, as expected. Right, I'm kind of running out of ideas on this. I'm going to take the motherboard out and see if I can see anything on the back. I think the back of this board is going to be mostly empty. Modern motherboards like this, they tend to be very mostly one-sided load. There might be a couple of token gesture passives on the back, some resistors, some tiny capacitors, but I'm not expecting anything of any real importance. We should check because we might find a crap ton of liquid damage back there. We might find a hole in the board, but I'm not expecting to see anything, which is why I hadn't taken the board out yet. But I'm not sure what this is, and if it's not what you think it is, then it has to be something that you don't think it is. And I don't think it's on the other side of the board, so let's go and have a look. Oh. Okay, there's quite a lot going on the back of this board. I stand corrected. Right, okay. So there's a couple of bits of... This is the back of the area that we've been looking at. I'll try doing some probing there. If that doesn't work, I tell you what I'm going to do. I'm going to inject on this line and see if something heats up. I don't think it's that regulator. We haven't got a short circuit. So we're not expecting a capacitor to heat up or something like that. But if that's the 3.3 volt rail, we might have a busted PCH or something like that. And if we inject a volt at a couple of amps or something and the PCH heats up, that means we can probably blame this on the PCH and call it a day, which obviously is a no fix and kind of sucks, but it does mean that it does put me in a position where I can say, okay, I'm fairly confident that this is beyond me. So let's check that capacitor on the back there. 70 kilo ohms, quite a lot. All right, check these other small caps. 10K, all right. Ground. 4K. What's that inductor doing? 4K. Don't know what that is. Small thing. See, the problem is these are small bits that could be going into the back of the CPU, so low resistances are not unexpected. Let's try a different strategy. I'm going to put the board back in the laptop, hook it all up again, and point that thermal camera at the PCH with the heatsink off and see if we get any pulses from the PCH. We don't need the display for that. Okay, power on. There's our pulsing. Oh, I should have done this half an hour ago. So there's our pulsing regulator. There's our dead PCH. Right, I'm back for another recording session with this laptop because I actually walked away from it. I actually recorded an outro saying I think the PCH is dead, but I'm not super sure because it's not really convincing, but I've got nothing else, no other leads. And I walked away and actually edited the video, but then I had a change of heart on this one because I thought, you know what, there was one area where we had some leads that I really didn't follow up on. The left I/O board. So there were two major things that I didn't follow up on with this. Is number one, at the beginning of the video, if you recall, the SD card controller chip had some heat in it. And like, I can't see a world where this would prevent the laptop from turning on, but also at the same time, it was getting some kind of power when we plugged in the charger because there was some warmth there, so something had to be going on. But also there was a bit that I omitted earlier on, is I actually tried disconnecting the left I/O board, and this happened. So with the board disconnected, if I plug in a charger over here, plug in, and as you can see, our oscillations are gone. So what does this mean? Well, the reason why I omitted it earlier on is that if we come in and we measure that that regulator again, there's still no one at home. It's not oscillating anymore, but also it's not outputting any power either. So I omitted this earlier on because I didn't think it was relevant. But maybe we can make something work here. So let's just go a little bit deeper. Now, I came in and I was prepared to just rip off that chip. But something else I wanted to try is just what happens if we just unplug some other stuff from this board. And the only thing we've got here is this, this little flex here. This is the fingerprint reader. So let's just take this out, take this board out and have a closer look. So there's our power button, and this works the way that it does on a lot of modern laptops. Is that's the actual power button, and the fingerprint reader is just a cap that sits on top of it. And this is a common setup on a lot of modern laptops because it means that the fingerprint sensor is an optional part of the laptop. They can do a version without the fingerprint sensor because the physical button is still there. You just put a dumb keycap here that doesn't have the sensor in it. So what happens if we just plug this in then? I'll just put this packet under it to make sure it doesn't short against anything. All right, fair enough. So we've got some milliamps again. Is this enough to get us power? Still nothing there. But if I push the power button, the laptop turns on. So there it is, folks. It was the fingerprint reader. But wait, there's more. Because then I was like, okay, well, I guess we'll buy a new one of these then, right? And I thought, I wonder what's under that little bit of black plastic there. Let's have a look, shall we? What's that? A tiny piece of corrosion. Say it isn't so. So under that black plastic, we have a conformally coated control chip and just a little bit of corrosion on that capacitor there. Right, so I'm going to call the fingerprint reader dead. Because that's all conformally coated and everything, I'm not going to try and dig into that. I wonder if we can find a replacement one. Let's have a look. And the answer to that was no. I'm not seeing one on a cast around. So what I'm going to do for now is I'm going to leave this unplugged. This laptop has actually come in from another store. And what I will do is I will say to them, if you want to make that fingerprint sensor work again, I'll leave it up to you to track down a replacement one. We have it working. I'm going to plug all of this in, and then we'll just see the laptop turn on and work, and then we can say we're done. See you in a moment, folks. One power light, one post screen. There we go, folks. This one was a big old red herring, and you know, I'm actually kind of annoyed with myself because in a previous video we had a laptop which a previous shop had given up on when it was just as simple as a replacement keyboard. And on this one, I basically made the same mistake where I went up the garden path looking at voltages and lifting regulators and stuff like that, when actually if I just sat down and just started doing systematic bare boot unplugging parts of the board, we would have found a solution much quicker. So I'll leave in all the guff because it's all interesting stuff on how to look at regulators and circuits. But yeah, thanks for tuning in, everyone. Oh, the battery looks like it's knackered. That's probably overly discharged. Are we going to look at that? Oh. Let's have a look. So I plugged the battery back in, but it's not being recognized. It's probably overly discharged. Also, that connector feels rubbish. So I'm going to plug this battery into my NLBA, which is one of these guys. This is a battery analyzer, and it tells me if it works or not. Okay, so to connect up our battery to our battery analyzer, we're going to need a wiring harness. So I've got a wiring set here. These come with the NLBA one. This is kind of turning into a slight pimp for the battery analyzer now, but I haven't done one in a while, so it's worth noting. Anyway, so that's going to plug into there, and then we need to set up all of these wires into this Phoenix connector that goes into the battery analyzer itself. So we need battery plus, clock, data, and ground. So on this one, it's pretty easy to figure out that the red is going to be our positive, black is going to be negative, and then we've got these three in the middle, and those three are going to be clock, data, and something else. And that something else might be a not used pin, or it might be a system present pin that needs to be connected to ground. Now, the NLBA1 software does have a pinout finder, but I've already checked and this one isn't in it, or I couldn't find it anyway. So we're going to figure it out. So that's going to go into there. So our first three wires are going to be our positive cables. So let's pull those out. And we're going to put those in our positive connector. Then we're going to grab the last three. And those are going to be our negatives. And now for the for the data lines, I'm just going to take a stab in the dark for these. It doesn't matter if we get these wrong. You can just brute force this until you figure it out. So I'm going to start with blue being clock. I think I'm going to go with blue clock and green data. Let's try our luck. And if this doesn't work, then we'll swap them around on the fly until we get something that does work. Alright, so the only wire that we haven't plugged in now is our sysdetect. Well, maybe sysdetect. I'm going to leave that floating until I've figured out what it is. So let's hook this guy up. I'm just making sure I've got my positive and negatives the right way around. Yes, I have. That goes in there. And let's get the battery analyzer in view. Alright, here is the white box. So that's now going to plug into there. And straight away, the observation that I would make is our output light on the front of the analyzer has not come on. So that means the battery isn't outputting anything. Let's try and connect to the battery in software and see if we get any response from it. So over in the software here, I'm now just going to do read all once. And we get nothing. Okay. So what I'm going to do now is I'm going to just try holding that sense pin, that mystery pin to ground. And the output light hasn't come on, but let's go for a read. No? Okay. Right. So now what I'm going to do, I'm going to try and swap around the I'm going to swap around the clock and data lines in case I got those wrong. Try it again. Still nothing. Okay, so what might be happening next is if the battery is really stone flat and has zero power in it, which is possible because remember it's been trying to power that regulator forever. Basically. So the battery is probably critically discharged. So I'm going to apply just a little bit of power to it with the apply output voltage. And what this is going to do now is it's just going to feed just 6 volts back into the battery, which hopefully will power up the BMS, the battery management system in the battery. And that means that we'll actually get a response from it. So let's try again. Nothing. Okay, so while we've got it powered up, I'm just going to go on dynamic. So it's just going to keep strobing the battery now. There it goes. And now what I'm going to do is I'm just going to start stabbing wires until we get a response from it. So I'll swap the clock and data back around again, just in case I had that right the first time. There we go. Alright, so that was blue and grey. So that is blue clock, grey data. Okay, right, so let's stop reading for a sec. And I'm just going to power off, and I'm just going to try and read again. Yeah, there we go. We've got a full read on it now. So we might not have needed the output voltage then. I have a suspicion we didn't need that. And it was just sulking because I didn't have the correct combination. However, now we've got a read on the battery, we can look at the status of this thing. So firstly, as you can see, the charge state is dead flat. It's stone empty. Health is at 100%, which is great. The battery is in good condition. Now, the bit that interests us is this is a 2-cell battery, and the cells are at 2.8 volts each. That is critical discharge. So in a LiPo battery, your cell voltage should be between 3.0 and 4.2 volts. 3.0 being flat, 4.2 being full. And the nominal is 3.7, which is about in the middle. So most people will say that a LiPo battery is 3.7 volts per cell because that's the middle ground, which is where the cell wants to be. Now, if you go below 3.0, that is known as over-discharged. But you can, from 2.8, that's not too bad at all. 2.8 is low enough that the laptop is probably reading this as a dead battery. However, we can easily recover this using the NLBA. So this is why the NLBA is a really good bit of kit, because without one of these, you would have to just simply assume that the battery is dead and replace the battery. However, with this, what I can do now is I'm going to go over to charge, and because we're in critical discharge, I'm going to give it, let's see, I'm going to give it 500 milliamps, which is as low as we can go. And I'm going to say, please just charge this thing up to 10%. Start charging. And what we're going to do now is we've put in a charge current of 500 milliamps, which is really, really low. And we're just going to very, very slowly bring those cells back up to a sensible voltage again. So I've told it to go up to 10% total charge. And once we get to 10%, we can then give it the beans, because we then should have just recovered it. But we're just going to very gently just massage the cells back up to a working voltage again. The other thing that we can do here as well is that once a battery has been over discharged, what you should do is recover it and then just let it rest and see if it droops again. Because if we take it up to 10%, then if we take it off charge and the voltage just goes down to 2.8, that means it's toast. However, 2.8, like I say, that's pretty tame. I've recovered cells from like 1 volt and they've been fine. If you've got cells that are at 0, like actual 0 volts, you're done. That's toast. Don't try and charge that. You might be able to, but it's not a good idea to try and recover a cell from 0 volts. So yeah. However, 2.8 is tame. This should come good. So this charge is going very well. Our cell voltages have come up to 3.25 and rising. And it's quite happily accepting the current that we're giving it. So you could look at this and be like, oh yeah, give it the beans, start banging an amp into that. But that's not a good idea when you're recovering from a critical discharge, because what is going on inside a LiPo battery is you've got 2 electrodes and you've got a polymer layer between them. The electrodes have a coating on them, a chemical coating, and that coating, when the battery wears down, the coating breaks down on it. And when the battery is at full charge or full discharge, that is when the coating is most vulnerable, because all of the chemical reaction, all of the ions, I don't know the chemical science of it, but all of the stuff is on one side of the battery, leaving the other side fairly exposed. So when you're at 3 volts, it's fine. But when you're in a critical discharge, that's when it's vulnerable to damage. So we want to just ease it up out of that dead zone before we start banging several amps into it to charge it at normal speed. All right, we're at 3%, but also I need to go fast because I've got stuff to do. So I'm not hanging around for 5%. So I'm going to hit stop charging. And I'm going to smash 3 amps into that. All right, so we've restarted charging. Our cells are up to about 3.5 volts now, so that's very healthy. And as you can see, our current now is just going to go whee up to as much as the battery wants, or 3 amps, whichever comes first. And what we'll find now is that because we're now smashing significantly more current into it, the actual charge rate is going to go through the roof, and we'll hit 10%. Probably in 5 minutes now. Yeah, that's topped out at 3 amps. That's fine. One more thing that I hadn't mentioned that I should point out as well is when we're recovering a battery like this, we do want to keep an eye on the individual cell voltages. They should be the same. So what we're seeing at the moment is we've got an imbalance of 3 millivolts, which is fine. I think we only really care once we get to like 15 millivolts or more imbalance. that's the point where you should be paying attention. However, thankfully, the software here will highlight like green, orange, and red. So we've got a green number, which is fine. But if we were seeing a high imbalance where one of the cells was noticeably lower than the other one, it probably means that that cell is knackered, which would also imply that the battery is toast and you should replace it instead of trying to recover it. But yeah, this battery is fine, it's just over discharged. Right, that's another 10 minutes of charge and we're up to 7% now. So as you can see, we've already smashed in like twice the amount in 10 minutes that we put in 30 minutes on the first run. So that's the power of high current charging, everyone. Right, so let's hit stop charging. That's close enough for me. We're going to plug this back. We're going to plug the battery back into the laptop and see if the laptop recognizes the battery and charges the battery. So let's disconnect that. There we go. Right, it's giving 100 milliamps now. I'm going to wait a little bit of time and just see if that steps up to charge current. There we go. 3 amps. There's charge. Oof. It did me a spook. It did me a heckin' spook. We're done. We win. The battle is fought and the war is won. And there's that nice big step up in the current as the battery bangs on charge as well. That's what we want to see. Excellent. Right. Another last minute adventure there. Thank you very much for tuning in. This one was a bit of a marathon full of red herrings, but also nice saves. So I hope you guys found that interesting. Thanks a lot for tuning in, and I'll see you all next time. Bye for now.